Hello everybody, welcome back. So we've been talking about mods. Last time we proved proposition 2.15. It says if A is congruent to B mod M. Do you remember what that means? A congruent to B mod M? Well, it had a definition. Definition 2.14 says that A is congruent to R if M divides A minus R. So in this case, M would have to divide A minus B. Okay, well, that's kind of a confusing definition. It doesn't lead to much intuition. So that's why in the last couple of videos, we really tried to start developing that intuition. Looking at those analogies, looking at ways to think about it. There's the boxes metaphor, there's the clock metaphor. There was thinking about remainders first, and then thinking about, A is congruent to B if A divided by M and B divided by M leave the same remainder. Or the boxes, if you could start at A and add M a certain number of times to get to B, or alternatively subtract M a certain number of times to get to B, those would be signs, those are the exact indicators that A is congruent to B. Okay, so A and B are congruent mod M, C and D are congruent mod M. What this says is that, you see how the symbol has three lines, looks like an equal sign? Turns out it also behaves like an equal sign. You can add C to both sides, and it's still true. Or you can add C to one side and anything else that it's congruent to the other side. Likewise, you can subtract from both sides, multiply. But then what we discussed at the end of last video is, can you divide? Can you write A divided by C is congruent to B divided by D? And then we figured out, answer is no, you can't divide. Why can you not divide? First, what if A divided by C doesn't give you an integer? These definitions only apply to integers. There's no such thing as 2.7 being congruent to 3.8. That does not happen. Everything has to be an integer. So A divided by C, no guarantee anymore that you even have an integer. So that's one reason why you can't. But there were other reasons too. We said, okay, assume you have A times K congruent to B times K. Okay, so A, C, B, D, well, let's assume you have the exact same K on both sides, allowing you to actually divide out the K and be left with integers. Then is it true? And the answer was still no. The first example we gave was, what about if K equaled 0? You could have 2 times 0 being congruent to 3 times 0 mod anything. I'll choose mod 6. But you can't, but 2 is not congruent to 3 mod 6. So that's the start of it. You can't divide out if it equals 0. You could be left with things that are not congruent. Moreover, it's not only equaling 0, it's congruent to 0. You could have something that's sort of 0 in disguise. So if it's mod 6, think about any number that's congruent to 0 mod 6, like 6 or 12. If you had 2 times 12, that would be congruent to 3 times 12 mod 6, right? 24 and 36 are congruent. Mod 6, yes? 6 does divide 24 minus 36. Or starting at 24, you can add 6 twice and get up to 36. Different ways to think about it. Or they leave the same remainder. 24 divided by 6 leaves a remainder of 0. 36 divided by 6 also leaves a remainder of 0. So another reason why these are congruent. But yet if you divide it out, again, we are left with 2 is not congruent to 3. So you can, so for this thing, this is not a true implication because K could be 0 or K could be 0 in disguise, meaning it's something congruent to 0, mod 6. But is that it? That's where I left you last time. Is that it? Are there any other examples of AK times BKs? So what do I want? I want AK to be congruent to BK mod M. I want A to not be congruent to B mod M. And I want K to not be congruent to 0? Mod m. Can you find me integers a, b, k, and m for which all 3 of these are true? Pause the video and give it a shot. It's a good exercise because it will highlight, it might highlight some deficiencies in your understanding of mods. We all have deficiencies in terms of mods. I'm not saying that in a mean way. Every person who learns about mods, even people who have learned about mods for a long time, could misunderstand them. So, but that's the goal of learning and math in particular. You want to find the parts of your understanding which are incomplete or which are wrong, and you want to correct them. So trying to find this is a good way to test your understanding of mods. If you've tried a bit and want a hint, 6 actually does work as a mod. There is actually a way to do this. It is not true that the only way that this fails is for k equaling 0 or being congruent to 0. There actually are other ways it can fail too. In fact, there are a, b, and k that you can choose here for which this works. So 6 isn't too large, so maybe give it a shot. Okay, now the k, there are many k's that could work. Well, actually not many, there are some. 2 works, a times 2 and b times 2. Can you find an a and b? Because 2 is not congruent to 0, mod 6, so check, this one's good. Can you find an a and a b which satisfy these two? Let's see, I think if you have a being 5, let's see, 10 is congruent to 4 mod 6, right? And so let's make this equal to 4. 2. Okay, there we go. So that should be an example. Is 10 congruent to 4 mod 6? Yeah. You can move from 10 to 4 just by subtracting a 6. Alternatively, if you divided 10 and 4 by 6, 10 divided by 6 leaves a remainder of 4. 4 divided by 6 leaves a remainder of 4, right? This is 1. 10 divided by 6 is 1 with 4 left over. This is 0 with 4 left over. So, yep. Also, you go to the definition. Does 6 divide 10 minus 4? Does 6 divide 6? Yes, it does. And is 5 not congruent to 2 mod 6? Correct. So there's an example. So what is going on here? What allowed this example to appear? That's an important question for us moving forward, actually. And a hint is the other thing on the board, the definition of a prime number and a composite number. An integer p, at least 2, is prime if its only positive divisors are 1 and p. An integer n is composite if it is not prime. Okay. Another way to say that, i.e., means in other words, n is composite if n can be factored as s times t, where s and t are integers, and this is not just like 1 times t. They're strictly bigger than 1 and they're strictly less than n. So this is a thing in math. You can sometimes see 1 is less than s comma t is less than n. This just means s and t are both between 1 and n. Okay. All right. So, so why are primes important in this understanding? It's because 6 is not prime. It is 2 times 3. It's composite. And the k that you're dividing out shares some primes with 6. It doesn't have to be, so it's actually one of the primes. 6 is 2 times 3. K is 2. But it wouldn't have to be, it could be 4 or 6, or 6 would be 0. So 4 or 8 or 14, some number like that would also work to cook up a counterexample. And because they share a prime, there's something that happens which prevents which prevents AK and BK from always being different. So we'll get to this later. You'll understand this once we start over the next couple videos. But just to give you a little intuition now, suppose you had 0, 1, 2, 3, 4, and 5. So when you're working mod 6, these are the 6 options for mods. After this, things repeat. Like 6 mod 6 is the same thing as 0. 7 mod 6, same thing as 1. 8 mod 6, same thing as 2. So you can kind of think about these as being the only 6 options. So if these are like the A's and the B's, and we're going to multiply these all by 2, what happens? So what is, so this is A or B. So remember in the AK equal to BK. So K equals 2. K equals 2. And A and B are, these are the 6 options for A and B. And with K equaling 2, you're definitely going to be able to find an A and B, which are different, but when you multiply them by 2, you get something that's the same. Why is that? Well, 0 to, if A or B, so suppose A is 0. What is A times K? Well, 2 times 0 is still 0. So 0 turns into 0 when you multiply it by 2. What is, if A equals 1, what is A times K congruent to? 2 times 1 is 2. What about 2? 2 times 2 is 4. What is 3? 3 times 2 is back to 0. What about 4? 4 times 2 is 8. That's congruent to 2. And 5 times 2 is 10, which when you think in mod 6 brings you back to 4. Do you see? When you're looking at if K equals 2, A times K and B times K, the only options when working mod 6 are 0, 2, and 4. So there's definitely going to be a way to pick one A and one B that are different, because it's like the pigeonhole property, right? AK, so if A and B have to choose from this list, but AK and BK only have to choose from this list, you're going to get collisions. You're going to get 2 things in the same box. So my example was the 2 and the 5 turning into 4. But I could have instead chosen 0 and 3 turning into 0, or 1 and 4 turning into 2. And still we would have had an equally good counterexample up here. So I did the 2 and 5. So if A is 2 and B is 5, then AK is 4 and BK is also 4. Does that make sense? Another way to think about it is whenever you multiply something by 2, you get to an even number, which when you're working with another even number like 6, means that the only outcomes can be even. So that's another reason to think that you're going to get collisions. The pigeonhole principle is going to apply. You can't get an odd number to appear as the answer. But anyways, as long as you have 2 numbers pointed to the same spot, then those 2 numbers can be your A and B, and your AK is what they're pointing to, and their BK is also what you're pointing to. So that's a way to cook up a counterexample. Where A and B are different, you choose different things to start, but the AK and the BK are the same. Okay. So that's a little intuition there. But really what's going on is it comes back down to the prime factorization of 6 and how it relates to the prime factorization of K. So we have to understand primes. That's very important. So in that direction, how long is this video? I keep trying to find, where is it? Oh, 14 minutes. Okay, yeah, actually that's enough for this video. So I'll stop here. Next time, we're going to work with primes. We're going to prove a lemma. Our first lemma in the course, that's cool. So we'll prove a lemma with some facts about primes, and that will allow us to then move forward and prove things like precisely when is it the case that we can cancel a k from both sides. That's what we want to know. We know the addition, subtraction, and multiplication are pretty straightforward. The division is more complicated. What's the exact condition that would allow us or not allow us, we want it to be the exact condition to divide out the k and get something which remains true. Okay, so next time, so think about this. This is good intuition. Think about it. It's complicated, but hopefully you can start to wrap your mind around it, and then come back next time and we will prove some facts, prove a lemma about prime numbers. See you then.